So when we talked about this on Thursday, there are two ways that we can create new functions out of old. That's one way of putting it. And one is that we can add and subtract, multiply and divide two functions together. Do you remember the example I gave you from your major? What were the functions examples I gave you? Oh, there they are. Profit and revenue. Okay, and how profit, revenue, and cost is the example for you. Now, again, if I were talking to another discipline, pharmacy, chemistry, English, whatever, I could use other examples. But for you, the best example is this idea of profit, revenue, and cost. That's one example of how we create a new function called profit out of two existing functions called revenue and cost. We also talked about, why do we say divide by zero is undefined? So just kind of tuck that away as a little extra gem that I gave you that I know for years and years, all we say is trust me. It's called trust me math. Trust me. It's undefined. But until I found this little example and started sharing it, and I can tell you, it's probably about 30-some years ago. Also, I haven't told you my little thing that people often ask how many years I've been teaching at Drake, and my response is longer than you've been alive. Okay, so I started teaching in high school long before that, and that's when I found this little gem. So I keep that tucked away as an example of why we can't divide by zero. We also talked about composite functions. That's another way that we can create new functions out of existing. And again, remember, my whole focus in my life is I don't want to study something. I mean, some people get off on studying something just for the sake of studying it, and there's some thrill in that. But I really have found it necessary in all of my life to know why I'm studying something. If it is truly just for fun and joy and enjoyment, fine. But when it comes to math, I found a lot of my students really don't share that enthusiasm. And so it's important that we know why we're studying it. And so when we look at composite functions, where in your life, composite functions just don't occur here, but where in your life do they occur? And I gave you the example. Do you remember it? What was it, Nathan?
Put on your sock before you put on your shoe.
Yeah, there's two actions there, right? And you can't do one before you've accomplished the other. And the same thing happens here. We can't get into and work with function G until we first work with function F. We have to accomplish the task of the inside, and these are the terminology I use here, the inside function before I can work with the outside function. So composite, using the composition of two functions, is another way we create new functions out of old. There is now a third way that we're going to do that, and this is what we call an inverse function. An inverse function. Now again, I know you've studied algebra. Many of you have had many years, and some of you indicate you've had calculus before. But here again is something that we have what we call an algorithm, a process that we accomplish something with. And you have algorithms for everything in life. What's the steps I go through to drive over here? Put the key in the ignition and turn. All these are processes, algorithms. We have an algorithm for finding the inverse of a function. But I want to give you a different or an expanded view of that algorithm. When we look at an inverse, first of all, why do we even want to do an inverse function? Now, if you remember an inverse function, maybe you've learned you interchange the x's and the y's and then resolve for the value y. My question is, who cares? Why do you want to do that? Well, in life, when do we ever interchange? And again, I don't use x's and y's unless I'm dealing with xylophones and yachts. And so my thing is, when do we ever interchange the input and the output? Let me give you an example. If we have Fahrenheit, degrees. Anyone here from a country that's not using Fahrenheit? Have you traveled to a country that uses Celsius? Okay, so if you're in a country that uses Celsius and you want to, I don't know, I can't really compute and know, do I wear a sweater or not when I hear Celsius degrees, but if I can convert that into Fahrenheit degrees, I'm ready to go. So this is an example of what we would need to do. So, you might have learned the rule, you take 9/5 of Celsius and add 32. I got to tell you a little story. I like telling stories because it helps, I think, to bring out the fact that math is very much of an everyday occurrence. I had an opportunity, a very rare opportunity, to go with the church choir director. She was invited to go to Australia for a week and decided she wants to take the entire choir down for a 2-week tour, which she did 2 years later. So I had the opportunity to go to Australia, New Zealand, and Fiji in 1 week. Now, if you've flown that distance, it takes 15 hours from LA to get to Australia. But anyway, it was a fun trip, and we had a great time. We were with a bunch of other church choir people. Now, I'm a math professor. I know math. So we're in Sydney, and we're trying to decide what the temperature is going to be. Do we wear the jacket or not? And of course, in summer here, it's winter down there. And so what am I doing? I'm taking the Celsius degree, let's see, 9 times 17, divide by 5. Oh, shoot, what is, And I was working really hard trying to come up with the equivalent Fahrenheit. The choir people had the answer like that. I thought, how are they doing that? I mean, I'm supposed to know my math and be able to compute pretty well, but they were getting it like that. Now, this is not with inverse functions, but it's a way that we use math in everyday life and don't even realize it. What they were doing, does anyone know the fast way of computing? 9/5 is about what whole number? 2. So it's about 2. 32 is about what value rounded to the nearest tenth? Depends. 30. So they were doubling the Celsius and adding 30. It was a good lesson for me because I realized, you don't always have to have a specific answer if you understand what you're doing. They knew what they were doing. They were doubling the Celsius and adding 30. Hear what I was doing? 9 times 17, divide by 5, add 32. They came up with what? 17 Celsius is about what Celsius? Is about what Fahrenheit? 64. Jacket or no jacket? Probably a light jacket. Okay. Now, that has nothing to do with inverse functions. It has everything to do, though, with using math outside the classroom. But the inverse function comes when people from Australia or any other country that uses Celsius come up here, and what do they have to do? Convert the other way? Convert the other way, yeah. And so if I look at this function and I want to write it in function notation, I could probably do this. F of c, what's my input? And what's my output? Well, my output is the Fahrenheit, which is also, again, as I told you, the same as that whole expression there. These are equivalent. When they come to a country, people who have used Celsius all their lives, what are they trying to solve for? They want to solve for Fahrenheit degrees? They're given Fahrenheit, aren't they? They want to solve for Celsius. In other words, they want to solve for the input. So anytime you have a function where the whole function is, I give you an input, you find the output. I give you the 17 degrees, you find the 64 degrees. I give you Celsius, you give me Fahrenheit. That's the function in this direction. But when we have to turn it around, when all of a sudden we know the input, we know the output. We know the output, but we don't know the input. We then have to solve for the input. So in this case, if I just arbitrarily interchange F and C, it's not going to give me a reasonable answer. Because it would, let me put this in red because I want to make a point that it's faulty reasoning. If I go the rules that we usually use in mathematics, that is interchange the x's and the y's, I would interchange the f and the c, correct? My input and output. And then if I proceed to solve for the what was my output, okay, solving for, actually I want to, see, I'm getting confused already, because all of a sudden I'm thinking, wait a minute, up here I solve for Celsius, and down here, well, shouldn't I be solving for Celsius again? Well, no, because I interchanged those two letters. It would actually turn out to be this, which is not right at all. So here's what we're going to do. So I'm going to put a big X through that, because here's what we're going to do. We're going to solve for C. If I want to solve for this value right here, what's the first thing I would do? Well, I would say F minus 32 equals 9/5 C. And then I would multiply both sides by the reciprocal. That makes sense now. This doesn't, because all of a sudden it looks like I can find Fahrenheit. And the reason is we're going to use letters that make sense to us. X and Y, who knows what X and Y stand for? We don't. We often have to reassign them. So why use them? Why use them? Why not use P for profit, or C for cost, or R for revenue, or N for number of items? So when we look at our inverse, the inverse is right here. This is what we're trying to do with an inverse, is solve for the input. Solve for the input. And when we solve for the input, we are going to be reversing all of the operations. Notice this, that up here I added 32, but what did I do down here? Subtracted 32. Here I multiplied by 9/5. Now it looks like all I did was multiply by the reciprocal, but what happens when I divide by 9/5? To divide by a fraction is to multiply by its reciprocal. Yeah, and so that's why the reciprocal comes up there. So what we do then is not only we reverse all of the operations that we're doing for an inverse function, but we also reverse the order. In the order of operations, don't we say we multiply before we subtract, or add or subtract? Down here, though, the first thing we did was subtract and then do the multiplication. So an inverse function really just takes everything in an opposite direction. Okay, so the inverse function, explain what's meant by inverse of a function in your own words. Well, the inverse of a function would be to solve for the input. That's basically what it is. Solve for the input, we create a new function. Okay. Now, do all functions have an inverse? I should say it this way, because what I really mean to say, do all functions have an inverse function? Remember what a function is. We're going to go back to the basics in this class. A function. Situation in which every item in the set of inputs gets paired up with every item in the set of outputs, except what's the stipulation? Every item of the set of inputs can be paired up with how many items in the set of outputs? Exactly one. Okay? I can't make this one go down to another quantity. And so there are situations where when we reverse this, we don't get. So what if this case happens? What if these two items share the same output? When I do an inverse on this, when I do the inverse, what does this set become? They're not outputs anymore, they're inputs. Okay, and what we had as inputs now are our outputs. And so these two items are over here, and we end up with 3 over here. So to reverse this means that this matches to here, this matches to here, and to here. Is that a function now? No, because this item of the input has 2 outputs to it. Okay, what does it look like symbolically? If I have f of x is equal to x squared, and we'll say y equals f of x equals x squared. If I look for the inverse of this, I'm going to be looking for, and I'm going to take it as y equals x squared, what am I going to have to do to solve for x, the input? Now, again, I use x's and y's when I don't have anything in context, okay? So if I don't know if I'm dealing with apples or oranges, I use x and y. Okay, so what would I have to do to solve for x? Take the square root. So if I take the square root of y, now when you take the square root of something, what must you be careful about? Always remember that, what? What if I said 4 equals x squared? What could x equal? Yeah, positive or negative 2. So we have to do positive or negative in here to make sure that we remember that. All of a sudden now, we've got one input having 2 outputs. And so here we have this would then be a function, but this would be a non-function. Now let's take a look at this. Take your Inspires and go home, add a new document. And let's go to a calculator. I'm going to teach you one thing that we're going to be doing some of, and so a little more calculator work here. I want you to go to Menu and go to Actions and go to Define. Menu, Actions, Define. And we're going to define f of x. Remember where everything is. I got 2 models in my head. There we go. F of x. Now, whenever we do, we're going to graph this. Whenever we graph, we're going to have to use x. F of x equals x squared. And press enter. All it says is done. Okay. Now, if you're on the black model, the touch screen, you can just go to add a page. Or you can follow us and go home, and then those of you with the gray and white models, I click once, tab down until you come down to this word called graph, this item right down here. So just tab until you get down here. Others, you know, if you have the opportunity, we're going to put a graph on. And let me check on something. Oh, okay, I see now why it didn't pull up. You're on this page, am I correct? Okay, what we forgot to do, and so let's go back and I'll show you and then you'll know what to do from here on. We need to get back to this page right here. Did I show you how to get back and forth between pages? Okay, you see the control, and you see then you have clicks left, right, up, and down. Do a control left click, and that puts you back to page 1.1. If you do control right click, where do you go? Yeah, page 1.2. Okay, what we forgot to do was that, and I'm going to go forward here and show you, notice how down here it says f1 of x. I'm going to show you something. How many different functions can you put on this grapher? 99. Okay, we're never going to put 99 on here. So we have to identify which one. Now in the TI-84, we had y1, y1 of it, y1, y2, and so forth, same sort of thing, only we're calling it's in function notation. So let's go back. If you should still be sitting on this. Do you remember how we go up and grab or select a former entry? Use your up arrow key a couple of times until you get it selected, and then press enter. Now it's in an editable, where we can edit it. And I want you just to move back, move your, this whole thing back until the cursor is just between F and the parenthesis. You're going to type a numeral 1 so that it now reads F1 of x equals x squared. And press enter. Okay, now go to the graph page. Let me get back to mine here. Go to the graph page. There we go. Okay, it's going to be that way about it. There we go. Go back to the graph page, and you'll see now it says F2 of x. We want to go to F1 of x. Remember how did I show you how I moved it? Use an up on that click pad, and you're at F1 of x. Press enter, and there's our graph. Okay, now what is the visual that you've learned on how to tell if a graph is a function? Thank you, Matt. Vertical line test, okay? Which says that if you have a vertical line, it can move anywhere. Okay, let's go back to page 1.1. And let's define, so here we go again, menu, actions, define. And let's define F2 of x. Be sure that you're moving outside of the parentheses to put that equal sign there. Equals. Now, what we have to remember is that in this Inspire, we're not going to be able to write, as we had over here, x equals. We're going to have to go back and write it in the notation f of x, and I apologize for this. We're going to have to go back and use that. The Inspire uses that traditional notation, so you have to convert between some of these. So we're going to have to put in the square root, so control on the x squared key, and put that in. We're not going to be able to put in plus or minus, okay, but we're going to put this in and press enter. Let's make it easy on ourselves. We're going to go up, grab that last line we had there, bring it down, move the cursor. We're going to change the 2 to a 3. And we're going to make this the opposite of that. Use the opposite of key. Got it? Press enter. And it's done. What do you expect to see on the graph side? So go ahead on the graph side. I'm going to just take a look at what we've got here. I'm going to refresh it here. How do we, okay, someone over here has already shown us part of that graph. Let's get both F2 and F3 there. So you're going to have to go on the graph side and make sure it says at the bottom F2, press enter, and then make sure it says F3 of x and press enter. Okay, we got one person over here who's got it. Let's see. Anyone else? Let's get everyone to do that. Very good. We're getting more people. Everyone, I want you to have that. Having troubles? Yes.
How do you get back to the thing at the bottom?
Oh, tab. Tab. I forgot to tell you that. Sometimes we find that by mistake. Okay. So let's see what we've got here. Okay. I'm going to wait until everyone gets that. Now, there's many ways that I can take a participation. One is to do that little quick poll I gave you on, I think I gave you a quick poll, didn't I? Yeah. I can also capture all the screens here. So I'm going to give everyone a chance to get some participation points today, just by making sure they have everything here. Got a couple people. And another reason why I'm pausing is I want to make sure everyone can do this. This is important to be able to get. Yes?
I'm not sure what happened to my first function.
Okay, do you recognize which one yours is?
I think on the top row.
Okay, what I want you to do is tab and find F1 of X. Do we still have F1 of X defined?
Yeah, I got it.
Okay, right from right where you are, type X squared. We can do it that way too. Okay, who is this person? I see some people working. That's you? Okay. So you want to tab and find F2 of X and then press enter and tab and find F1 of X. Looking at these, can we tell that that the second one is not a function? If we did that vertical line test, it would enter through the, and again, we have to realize that we're not able to draw a non-function in a function grapher, and so we have to break it up into two parts. Okay, are we getting successful on this now? Almost. I'm going to ask, I don't know who this is, I'm going to make this person the presenter though. I can't have all the fun up here. So I don't know who this is, so everyone's got to play along until we find out. Sometimes what we want to do is to identify the functions in a way that we can tell which one it is. So what I'd like to have you do is press menu, where everyone do this and we'll find out who this is. You're on actions, so open up the menu of actions, go down to attributes, and press enter. Okay, now you see this different kind of an arrow. If you look at this, it says graph F2. Okay, I want you to press enter. And it pulls up then a way that you can change the looks of anything. And of course, things will be different according to what the object is. But this has a little arrow, so use a right arrow. We should open up this menu. Okay, so there its line weight is medium. Do the right again. Go to the right again. Now it's thick. Okay, so we can change the thickness of that. Go down. Use a down arrow, and here's continuous. Do a right. Now it's dotted. Okay, do a right again. Now it's dashed. Okay, so you can change the attributes, and we do this sometimes with points. For example, if a point is, we want to indicate that a point is there, but it's not really a part of the function. It has to be an open circle. We can make it open. Now we're not going to open the circle because we don't have a point that we're dealing with. But if you were changing the attribute of a point, we'd have the option of making the point either open or closed, square or round, large or small. I mean, there's all kinds of things we can do. So how do we get into that? Menu. Good. What's the next step? Actions. Yeah, actions, and then always go to actions if you want to do something that's not really mathematical in nature. You just kind of like labeling or something. Okay. I'm going to stop that person from being the presenter. Thank you very much. And let's go on with our lecture. Because our lecture today is talking about inverse functions. Again, I know you've had these before. Hopefully what I'm giving you is just kind of adding to your knowledge base about this and maybe helping you understand them a little bit better. Let's go on and look at, I did that. Okay. Oh, by the way, if you look on page 76, the steps on page 76 are those traditional steps that say always interchange X and Y. I don't like that. And by the way, when we are looking at the symbolic view of this. This is one way of writing the function. Actually, we probably should do a different letter like g of x. Another way, and some of you know this, another way of expressing that this is the inverse of this would be to say this. Now, in another context, what do you know about the negative 1 exponent? If I said 3 to the negative 1, yeah, you take the reciprocal, right? And that's why I don't like that. I don't know who made up that symbol. They didn't ask me because I would have told them. It would tell me confusing years later. But someone years and years ago decided that that would be adequate for the inverse function symbol. So just be aware. It's something that I don't like, and I don't intend to ever use it extensively. Instead, let's think about what happens out in life. Out in life, you've got a payroll program that says, give me the number of the hours the person works, and I can give you back the pay they need to get. Give me the hours, I give you the pay. Give me the hours, give me the pay. And all of a sudden, someone comes up with, well, wait a minute. If I want to get $35,000, how many hours do I have to work for that? Whoops. My input was hours, my output was pay. Now you're telling me the pay, and I now have to go back and do everything in reverse to come up with the hours. That's an inverse function. So just kind of look around and, look around for composite functions. Look around for that where you are adding two functions together or subtracting or whatever. Look around and realize how many inverse functions you have in your life. Okay, well, let's go on. We've already talked about this. If I'm going to, I'm going to set this equal to y. If I'm going to find the input or the inverse of this, my first thing is solve for x. So we would have y squared equals 9 minus x squared. Y squared minus 9 equals negative x squared. The opposite of y squared minus 9 equals x squared. X equals plus or minus the square root of negative the quantity y squared minus 9. Now this brings us then to another situation. If I've got that negative there, what do we have to be careful about with square roots or any even root index? What do we have to be careful about? Such as? Can't be done. Because we're asking the question, what value multiplied to itself twice is going to give me negative 2? And of course, we don't have anything. Okay? So we're going to have to be very careful that when we find the value of y, that y squared minus 9 becomes a negative, so we can take its opposite to make it a positive. So we have to be careful about that. Okay, inverse functions come up with that. A fourth way that we create new functions out of old ones is to use those transformations. You've studied these before too, where you take a function and you move it to the right, you move it up, you reverse it or find the reflection of it. You take the function and you make it wider or you make it narrower. Okay, those transformations we are talking about. So if we're looking at the square root of 6, we want to translate it up 3 units. Now, let's think about this. I'm going to have you take your inspires, and what I want you to do, we're going to do a new problem. Now, a new problem means that I can start over with F1. I don't have to keep adding on to F4 because it'd be confusing. So I'm going to, if you're on, well, let's just go home. This, no, I'm sorry. Oh, this is a good example. When I do something like this and I don't mean to, how do I get out of it? Happens to all of us. One way would be, you see this thing saying current? Okay, we just do a current, go back to the current one. If you do escape doesn't work. Control escape often works, but not in this case. So the only thing we can do is current. Okay. What I want to do is to insert a new problem. So I'm going to go to document. Now, if you're on the gray model, what you'll do is, let's see here. I've got to stop and think what I want you to do here. Yeah, control home. Control home on the gray model is the same as document on the black model. And you see this thing called insert, and we're going to insert a new problem, not a new page. What happens is we add then, and let's add a calculator. I'll go back on that and help you out with that here. If you're on the black model, do document. If you're on the gray model, do control home for that. And if you get in there, you get down to insert, and then you can insert a problem. Okay. What we have here is on 2.1, a completely brand new problem. It has nothing to do with problem 1. It's kind of like in the textbook or on the web assign. Problem 4 can use f of x. X is an input, f of x is the output, just like problem 1 can. They don't mean that they have the same value. Completely different problem. And that's what we can do here. It's a completely different problem. Okay, let's go to menu. Oh, did you add a calculator page? Okay, menu, actions, define, and we'll define f1 of x again. Only this time we will make it square root of x. And enter. Okay, we're going to add a graphing page. Remember how we did that? We can go to menu. I'm sorry, home. You can go to menu, but I want you to go home. Pick up a graphing page. And if we go up one step, we'll have our f1 of x. And we'll press enter. So there's f1 of x. By the way, how do we change the window? We did that on the 84. You all knew how to do that. Menu, window, window settings. Okay, it's all right there. If you're on the graph page, you go to menu, window, window settings, and it's just like we had before. Okay, we're not going to change the window at this point. I just want to make sure everyone knew how to do that. The problem that we have in our work here is to translate up the function 3 units. Now, if I'm going to take this function and move it up 3 units, which of my variables am I going to change? My input values or my output values? I want to take this function and move it up 3 units. Am I going to change the input or the output values? I'm just going to move this up 3 units. Yes, input or output? I see that hand. Your hand's not up, Taylor? No, okay. What's it going to be? We're going to change the input? We're going to change the output? Alan's testing out the intonation of my voice here. Yeah, these are some things that we've done before. I know if I went back to the notes and I said, what is g of x going to be? I think everyone would get me the right answer, which would be what? Translate it up 3 units? Plus 3? Okay, well, let's look at this. What did I say f of x represents? The input or the output? f of x, the output. Now, the input is x, the output is f of x, and that equal sign says what is on the left side has the very same value as what is on the right-hand side. So that means this whole expression is also an output. Now, if I take the square root of x and I add 3, am I adding 3 to the input of f of x or the output of f of x? Go ahead and say it, Nathan. The output. Absolutely. So, back to the graph. If I move this up 3 units, which variables are changing? The input values or the output values? The output. Because the only thing I'm doing is taking the outputs of function f and adding 3 to all of the output values. So let's go over here. Press tab. Well, let's go back to page 2.1. We're going to use our Inspire to create this new function. So let's go back, menu, actions, define. We're going to define f2 of x. There we go. f2 of x. And it's going to take what part of the function f1 of x? Input or output? The output. Okay. What do we name the outputs? Well, how about f1 of x? It's going to take everything of f1 of x, all the outputs of f1 of x, and do what? Add 3. Isn't that what we said we were going to do? f1 of x is a name for the outputs of function f, and we're going to take all those and add 3 units. Okay, now let's go to our graph, tab, make sure it reads f2 of x. Where do you expect to see f2 of x? 3 units up. Bingo, there it is. Okay, there it is. So we have now successfully transformed, we have created a whole new function. When you look at costs, what is cost comprised of? 2 parts, right? What are they? Business majors, come on. Variable cost and fixed cost, okay? Your variable costs could be things like the square root of x or whatever it would be. The plus 3 would be equivalent to that set of or that value of your fixed cost. Okay, same idea. We've taken the variable cost that we now have to add on to it, which is now going to, is it going to change the number of units you are creating? No, it's just changing the output of that same number of units. Okay, so the vertical translation looks like that. The horizontal translation, this is a little trickier. The horizontal translation says, I'm going to do the exact same thing I've done before, that is take the square root, but now I need a new input. And my new input is going to have to be, now I'm going to the left, so I'm going to have to say x plus 4. And without going into all the details about how that happens, we'll just let it write at this point, x plus 4. So if I want to, let's go back over here. If I want to define a new function, menu actions define, we'll define f3 of x to equal. Now I can't just say f1, well, could I? Could I use f1 of x in any way? What do I want to put in place of the input in here to move it horizontally? Left. plus 4. Okay, so let's test it out. X plus 4. Now, if we are correct on this, when we graph F3, we should see that original graph move to the left 4 units. What's changing, the input or the outputs? Now, you might say both, okay? But, I'm going to say enter here. But when I look at this, if I'm going to pick up, and by the way, I need to do some, I'm going to do actions, remember those attributes? I'm going to change this to be just a little bit different so I can always keep my eye on what F1 of X is. If I move this 4 units over, what I'm saying is that when the input is 0 here and the output is 0 here, I get the same output when the input is what? Did I do that right? Well, we're going to send right and see. Now, keep your eye. Did you see this up here? We're still in attribute mode. How do I get out of that? The last command I gave it? Escape. Always escape. Okay. So now I'm going to hit tab. Did I do this right? And you know, you're going to find out that sometimes I don't. You know, I make mistakes. We all do. Let's see. Oops, that did go over there. Okay. But what happened? The input, well, the input was X plus 4. Move that down here. The input is X plus 4. What did X have to be? X is 0 here. What did X have to be in this one? Not 0, but -4. Yes. And when X is -4, it has the same output as when X was 0 on the original function. And that's why I had to add 4 to that. So did I change the outputs? Not really. Because now I'm saying that when the input is -4, it has the same output as when the input is 0. When the input is -1, it has the same output as the input being 1, and so forth. It looks a little different, but that's what's happening. To do a reflection, what do? So if I do a reflection, we'll say R of X. It would be leading coefficient changes. So it would be negative the square root of X. And if I do a vertical stretch, I'll say V of X. I'm going to multiply by a factor. Okay? So we can test those out if we want to. One thing I want to make sure I show you, because it does come up, and I realized on the video from the last semester, I didn't really explain how to get into this. So let me show you something with this. Let me just give it a minute of thought here. Let me try it and make sure that it's what I want it to be before I tell you. Yeah, okay. What I want you to do is we're going to, remember on the 84 you have the table feature where you can compare values side by side and so forth. Remember that on the 83, 84? Okay, we're going to do the same thing here. So in order to do that, I'm on the graph page, and I was trying to remember where in the menu it happens. And so if we go to menu, let's see, maybe under view. Yeah, okay, let me show that again. Go to menu, go to view, and you've got this show table. And again, if you like the shortcuts, it's Control-T, T for table. Okay, when you do this, you create, or it splits the screen into 2 pieces. And so now over here is that graphing page that I have. And over here then is the table that we want. Now let me, and again, this is going to come up in the video for section 1.5, so I just want to make sure you understand. How did I get there? I just was on the graph page. You might want to write this down. On the graph page, and I did a Control-T, or I went into menu, view, and it said show table. Okay, now the other thing I needed to explain is that you notice, look at my screen, do you notice how black the border is around the graphing page? And if I press menu, can you tell that I'm active in the graphing page? That's the menu for the graphing. Okay, now how do I get over to the table? The table is Control Tab. Control Tab is going to switch my activeness to the other piece of the window. So Control Tab. Now if I hit menu, I have a completely different menu that comes up. And if you want to change anything about the menu, come down to table, and then you can edit the table settings. And this is where you are familiar with the 8384, hopefully, where you can, let's start the table at 0, or let's start the table at 10. Let's make it, and tab, let's make it move, let's make it jump every 10 input values or every 1/10 input values. You can change that. Or sometimes, as we do, we come down here to the independent and we ask, and that means then that everything's blanked out. And now if I say, okay, the input is 1, what is the output? I can then just put anything I want in there. I think I need to go through that one more time, although it will be on the video. Let me go through it one more time with you. I'm going to get out of that by hitting escape. I make sure that I'm active on this window, on this side. I know that I'm active. A couple ways I can check. The border is very black, or I can go to menu. If on the other side is a graph, you know what the menu, hopefully you know what the menu looks like for the graph. How do I switch between sides? Control Tab. Okay. Once I'm in here, I go to table, edit table values. If you tab, you can get to any one of those. Now if you're on the touch, those of you with the touch model, have you been successful using the little, so you can just move the cursor down there and press enter, but if you don't, you can always tab, and once you're here, you want to go down to ask, we can do that, and now notice everything is blanked out. So now if I want to know what is the output when the input is 0, I can say what is 0 there. Now, didn't I have 3 graphs? Where are the other 3 graphs? Well, let's see, I'm going to try something. By the way, the best, if you don't know how to do something, if something isn't where it wants to be, do you have the sense of just giving it a go, trying it? You got to have that. You're not going to break it, okay? Trust me, you're not going to break it. So if you think, where is that? I wonder what it is. Give it a go. It's like a table on the in the computer. If you can't see all the cells, all the columns in a spreadsheet, what do? You probably just kind of use the right and cursor over into it. Same thing I'm doing here. I'm just going to cursor over, and there's F2 and there's F3. Okay. Again, it's going to come up in the video, and I didn't have, let me explain this very quickly. Last semester, I didn't have the ability to load anything on YouTube more than 15 minutes in length. And so I had to take all of the class videos and break them into less than 15 minutes. Every now and then, you'll hear me say on the video, oh, shoot, I went over 15 minutes. And if you happen to notice the counter, you'll see that maybe it's 15 minutes and 3 seconds, which means I have to then go in and edit it and chop it and get it ready to put on YouTube. And so what I did for you is I merged all of those together, so you don't have up to 1 million little 15-minute videos to go through. You have maybe 2 to go through that are maybe 45 minutes long or whatever. So I got into that, by saying that when I chopped it off and when I stopped the class, I keep talking, and sometimes things didn't get recorded between the 2 videos. And so this is one thing that didn't get recorded, was how we got into the table. So now you've got today's video you can go back and look at. And then when you see the video for 1.5, if you remember this, you're ready to go. If you don't, you can always go back and view this and see. Remember, it's about 54 minutes into this video that it happened. Okay. Let's then go on in our lecture notes here. Weekly cost of producing n units in a manufacturing process is given by this function. C of n equals 70n plus 375. The number of units produced in T hours is given by, so here's another function. Okay, so I have the number of units produced in T hours is given by this. I have the cost as C of n. Now, which of these ways of creating a new function am I demonstrating with this problem? Is it adding or subtracting two functions together, multiplying or dividing two functions together? I'll be real careful with that. If it were multiplying, it would have C of n times n of t. Okay, so no, it would not be multiplying, but it's a very common way that we think about it. So it's not multiplying. So what else would it be? We are making a substitution, and in which of those did we make a substitution? Someone said it? In addition, you said? If it were addition, I'd have a plus sign between those two functions. Okay, let me focus you a little bit. N of t, is that N of t, does that represent an input variable or an output variable? N of t. Output. Okay, what's the input? See, this is a function all to itself. So what's the input of this function? Someone said it. T. Yeah, the input is what's between those parentheses there. Okay, now I could, or this problem could have been written this way. N equals, and we do this often in mathematics. It's like when I did the Celsius problem, I said, Fahrenheit equals, but then I went back and said, but I could have said F of C because C is the input. Okay, so we could say this. Go back to this one now. Whoops, let me pick up something here. Go back to this. That expression right there, C of n, input or output? Output, okay. What is the input? N, okay, so the input is n. What's another way of writing n? N stands for the number of units. Here it says again, number of units. That's the same thing, right? Only it's defined by N of t. So if you take a look at this, I'm going to put this in the color. Here's the N of t again. When we look at this, and we see C of, what is the expression within this set of parentheses? It's always what? The input or the output? It's the input. If it's within the parentheses like that, this is our notation that we have to understand in order to be able to move forward in this course. This is the input. Now, the input is N of t. The input is n. But N of t is its own function. Am I giving you the hints enough? Which of the four ways of creating new functions are we talking about? It's not the arithmetic operations, not add, subtract, multiply, divide two together. I'll give you a hint. I'm not interchanging the input and the output. I'm not saying let's solve for n. That's not the whole thing. We do solve for n down here, but that's not the whole purpose of this problem because it kind of throws everything together. composite functions. It's a composite function. The output of this function becomes the input of the second function. Now, if I'm going to complete this problem, what's the first thing I have to do? Well, let's write it this way. C of n of t is also the same thing as C of 40t. Where did I get 40t? Yeah, I just did a substitution there, okay? And when you said substitution, I said you're almost there. Okay, you got the right idea. If I have the input now is 40t, up here, every place I see an input, I'm going to put in 40t. So I have 70 times 40t plus 375. Now, if I want to find out what is the cost, I'm going to have to first know the hours it took to create that many items. So my first step is going to have to be computing this. Then I multiply by 70, and then I add 375. So this is an example of a composite function. Now, the other thing that happens here is that in the original form, what was the input? Well, it was n. But when I use the composite function, what is my input now? It's not n. And actually, if I use one letter, it's actually t. Okay, and the other thing we probably would do, we probably wouldn't, if we were going to do lots of these, we probably wouldn't multiply 40 times the number of hours first, and then multiply times 7. We probably would do 2800 t, and then add 375. Okay, we probably would do that. So this is an example of a composite function. Now, in the original one, it says, what's the cost of producing n number of products? 12,000, 1,500, 13, whatever. What's the cost? If I know how many units I have, what's the cost of producing those? What we come up with is, now we're not basing the cost on the number of units, we're basing it on what? Time, the number of hours. If I have a company now that can give me 5,000 hours of work, or if I have an employee who can, who can spend 5,000 hours of work over a period of time, how many items can that person make, and what's it going to cost me? And so that's what this is telling me. This is telling me that if I have the number of hours, I'll know how much it's going to cost me to make whatever number. I don't know how many items though. This is what I don't have now, is how many items I've got, but I can tell you how many hours I'm going to let someone work, or the company's going to work. Okay. Now, it seems like we take an awful long time on section 1.4. Same thing's going to happen in section 1.5 and 1.6. And that's why when you have these for the next 3 lectures, you're going to have the luxury of breaking it up and not sitting for an hour and 15 minutes maybe at one shot. But let me just tell you in the next 4 minutes what we have in section 1.5. Section 1.5 is what we call limits. And we deal with limits every day. Speed limits, eating limits, drinking limits, budgets are limits, and so forth. And what we have are 2 variables, an input and an output. We're going to have this from now on, okay? You're going to hear me say input and output all the time. So what we want to know is, listen very carefully. I know you're getting ready to pack up, but this is extremely important. And you'll hear it in the video, but I want you to see my expression as I tell you. When we talk about limits, what we're doing is we're saying as the input moves in a predictable pattern, 1 hour to 2 hours to 3 hours, as the input moves in a predictable pattern, the question we're asking is, wonder what's happening to the output. Okay? It is a math in motion. It's not saying what happened at 2 hours, at 3 hours. It's saying as the as the input, which we'll call time, as the time comes closer and closer to 3 hours, how many cars are passing by the street out there? Okay? And so we ask the question, what's the output doing? Now, we sometimes know, we can figure out the output is going to be 10, 12, 15, whatever, because we have a function, we just put 3 in and we get an answer. But sometimes, because of the mathematics, like dividing by, if I'm going to divide by, and what I divide by turns out to be 0, I can't do it. Or the square root, and if the square root happens to be a negative, I can't do it. But as I come closer and closer and closer to 3 hours, what value are the outputs getting closer and closer to? I don't care if it ever reaches that value. But what's it approximating? What's it getting close enough to that I could be, kind of guarantee that if I could go there, this is what I would get. Okay, that's what a limit's all about. Now, an extra credit opportunity is, and I have it, and I'll make sure that it's on Blackboard active for you, is that you bring in a PowerPoint presentation. I have it all labeled out. I tell you exactly what you need. But basically, you spend maybe 2 or 3 minutes before class starts, before I start class, and we talk about, you present and say, here's a limit I found in my life. I don't want it to be, I took function f of x and got the, I don't want that. I want it in your personal life. Where did you have a situation where you had some event or some value that was predictably every hour, every half hour, every day, every bite of food, I don't know, everything, every piece of item you bought, but you have some input that's, predictable. And the question you asked was, I wonder what the output value is going to be if I took it to that limit. Okay? So we find that we're taking the input to a limit, but we don't know what the output's doing, and it's also going to a limiting output value. So think about that. I'll make sure it's active for you. Again, the videos will be there. Please, please, please don't wait until the Monday night before to listen to 3 hours of lecture. You won't get anything out of it. Okay? Plus, it will help you with the homework to make sure you've got the homework ready. Ask me questions. Don't be shy. I will always be there to answer questions for you. But be sure that you are